Hi guys, and welcome to video number 22 in the But How Do It Know companion video series. And today we're going to be looking at in more detail at the ALU, load, store, and data instructions for our CPU. Let's start with the ALU instruction. So this diagram here shows in more detail how to construct an ALU instruction. So the first bit of an ALU instruction is 1. The next 3 bits correspond to the ALU operation that we want to perform. So these will be hooked up to the operation signals for the ALU. Finally, in the last 4 bits, we have reg A, which is going to be the input of our ALU instruction. Reg B is going to be the second input of the ALU instruction if it requires 2 inputs, and it's also going to be the output of the result of the ALU instruction. So let's look at the schematic more closely. So if you recall the previous video, we saw that steps 1, 2, and 3 of every stepper cycle are always used to load the instruction from memory into the IR and increment the IAR by 1. So we can see here that the ALU instruction is going to use each of the 3 remaining steps, namely steps 4, 5, and 6. So in this schematic, you will see references to reg A and reg B, and these correspond to a circuit that is described on page 119 in the book, and it is the register selection circuit. So basically what this circuit does is connects to the last 4 bits of the IR and decodes whatever registers are specified in there in order to send the signals to the proper register. So if you enable reg B, you can think of that as actually enabling the proper register that is specified in the reg B slot in the instruction. So going back to our ALU instruction, step 4, we're enabling reg B and setting TMP. So here we are basically setting up the second operator to our ALU instruction. In step 5, we are enabling reg A. So we're setting the first input of our ALU instruction on the bus. And this is where the actual ALU computation is going to happen, and we're going to finally save the result into the ACC. So in step 4, we prepare TMP. In step 5, we set reg A on the bus. Now both our inputs to the ALU are properly set. The ALU is always doing its computation in the background, and we are setting the result in the ACC here. In step 6, we are enabling the ACC and storing its result in reg B to save it. Below that, you see other gates that are there, and those are used to select the proper ALU operation. So you can see on the right, those AND gates are sent to the ALU up signals. So their job is to make sure that if the current instruction is an ALU instruction, then if we are on step 5, then send the values of bits 1, 2, 3 of the IR over to the ALU to select the proper operation. And on the right, the gates that are there are used to make sure that what we are doing in step 6, which is namely setting the result of the accumulator in reg B, we don't want that to happen when we are doing a CMP operation, because it doesn't produce a result. So those gates, that AND gate there, right before the NOT gate, it will turn on if all of the bits 1, 2, 3 are on. So we are doing a CMP operation, and then the NOT gate will disallow the AND gate to the right to turn on in step 6. So that's it for the ALU instruction. Let's move on to the load and store. So the load and store instructions are used to move data to and from RAM. The RAM address to be used is specified in reg A, and in the case of a load, the data is taken from RAM and written to reg B, or in the case of a store, it is taken from reg B and written to RAM. So the first 3 bits of a load or store instruction are always 0. Then if it is a load, bit 4 is set to 0, or a store, bit 4 is set to 1. Then we will have, as we talked about before, reg A and reg B specified in the last 4 bits of the instruction. Let's look at the schematic. So load and store instructions only use 2 steps of the stepper, step 4 and step 5. So if you look at the 2 top AND gates there, those are used for the load instruction. So in a load instruction, what we want to do on step 4 is enable reg A onto the bus and set its contents into the MAR. For step 5, we're going to be enabling RAM and storing the result into reg B. Now the next 2 AND gates show what happens if it is a store instruction. So for step 4, we are doing the same thing as for the load. We are enabling reg A onto the bus and setting it into the MAR. But for the 5th step, we are doing the inverse. So we are enabling reg B onto the bus so that we can set it into RAM and write the data there. The circuitry that you see below all that is used to enable all these gates here that we've mentioned before, only if we are doing either a load or a store operation. So this instruction selection circuit, as I call it, is described in detail in the book, but like the reg A and reg B circuit from page 119, we're not going to be using it in our design, so I'm not going to go into it in more detail, but just consider for now that the use of this is to make sure that whatever we've wired up here only takes effect if we have the proper kind of instruction in IR. Now let's check out the data instruction. So the data instruction is used to set a byte of data into a register. It always starts with the same 4 bits, 0, 0, 1, 0. Bits 5 and 6 are also always 0, 0 because the data instruction does not use the reg A parameter. And the last 2 bits, bits 7 and 8, contain reg B, so that is the destination where you want to store your byte of data. What's special about the data instruction is that it is a 2-byte instruction. So in RAM, it is expected that you will have your data instruction, and right after it, in the next RAM memory address, you will have the actual byte that you want to store in reg B. So the data instruction uses the 3 remaining steps, 4, 5, and 6. You can see at the bottom there is again the instruction selection circuitry that makes sure that all the connections here only take place when we are actually processing a data instruction. So the main objective of step 4 is to take the address that is in IAR and send it to the MAR. Because remember, in steps 1, 2, 3, we have loaded our IR and incremented the IAR. So the IAR is actually now pointing not to the next instruction, but to the data byte that is right after it in RAM. So that's what we want to save to the MAR in order to get it and put it in our register. But that means that we need to increment the IAR another time so that the next time that we go around the stepper, it will contain the address of the next byte in memory, so skipping over our data byte that is there. So all of this is happening at the same time in step 4. We're sending IAR to the MAR. We're also using the fact that it's already on the bus to set bus 1, increment basically the IAR, and capture the result into the accumulator. In step 5, we are enabling RAM and saving, so now we are saving that byte of data into reg B. And finally, in step 6, we are taking the result of the accumulator, which is where our next instruction is, and saving it to the IAR so that the program continues at the proper location. So that's it for the data instruction. So we've seen in detail the ALU, load, store, and data instructions, and it would be really cool if we could go onto our project board and try them out. But unfortunately, our control section is still not wired here, so even if we programmed instructions into our RAM and started our clock, nothing would happen because we don't have any control signals happening as the clock goes forward. So now we're going to veer away from John's book for the next two videos, and we're going to look at two new concepts that we're going to implement here in our control section, namely microcode and shift registers. I'll see you soon.